So what we'll do for the next 30, 40 minutes is try to juggle a presentation with the three of us, which is me, Jonathan, Max, Hohl sitting in the other screen, and Jeff Steadman as well. We'll be talking about the mineral geochemistry work that we've done over the last 3 years at Codes, part of the project. So but basically, I'm sitting in Canberra, Jeff and Max are sitting in Tasmania, so we'll see how it goes for the talk, and we'll have to juggle the three people to do that. So, okay, Max, can we get to the next slide? All right, so before we start, I want to acknowledge GSQ for getting the project started with us through the Strategic Resource Exploration Program. I also want to acknowledge Chinova Resources in Glencore for providing access to sample and data and a lot more as well with discussions and emails that followed the sampling. CSR for providing access to archive samples, especially GMustin to getting us access to some of the uncovered Cloutier samples that we'll talk about today, and the Codes analytical staff for the LAACPMS laboratories. So quick outline for the talk. What we'll do is a quick overview of what we've done, the main aims of the project, and then we'll move on to two different types of systems. The first one will be IOCG system, and we'll talk about SWAN, Starra, and Ernest Henry. And then we'll switch gear. We'll talk about sedimentary-hosted base metal systems, and we'll do a 5 minutes or so on Lady-Annie. And the report that we've produced for this project, you can see the link here on the page below. And on the right side is a nice photos of all of us that are presenting right now. So we cannot be there in person. That would have been great to be there, but this is still great to be able to talk to you today. So first of all, talking about mineral geochemistry as a vectoring tool. And the premise behind this is that many hydrothermal alteration gangue minerals are sensitive to changes in fluid chemistry and temperature. And this is something you can see here on the right image. It's an image of a pyrite grain. You can see sometimes the cobalt and nickel will vary together, like in the core of the pyrite, which you have kind of green and orange and red colors. They kind of vary together. But on the rim of that pyrite, cobalt and nickel are decoupled. So that means that these are processes that are forming this pyrite through time have differed or have changed. And the image as well below, you can see that there's a late overprint of copper in the cracks of that pyrite that's formed chalcopyrite to form mineralization. So there's different processes, different stages that we can map, and these are all sensitive to changes in fluid chemistry and temperatures. And we can do this for lots of different minerals. I use the example of pyrite there, but we can also do this for silicates, oxides, carbonates, and phosphates. And basically, the chemistry of these individual mineral species will enable us to characterize fingerprints and footprints of ore deposits. And these together can be used to vector two mineralizations in the IOCG system, and we'll demonstrate how we can do this now. So in terms of IOCG deposits, the locations of the deposits we looked at were from the Eastern Fold Belts, and the premise behind them is they form, here we go, here there's three ones. The main we're going to talk about is Starra at the bottom of the belt. There's SWAN and Mount Elliott a bit further up, and then there'll be the Ernest Henry deposit that we'll touch upon as well. And the premise behind these, looking at these IOCG deposits and studying them, is that they form voluminous hydrothermal alteration, like we've been discussing since this morning. It could be sodium, calcium, or calcium iron, potassium, potentially a bit of CO3, a bit of SO4 or PO4 alteration as apatite, sulfates, or carbonates. And basically, they form, like I said, voluminous and large alteration around these deposits. And the aim of the projects was to test the use of mineral chemistry to target to mineralization, or another term, can we do any vectoring towards them like it's been developed for porphyry systems. So to move on straight into the first deposit we looked at is the SWAN deposit. It's an IOCG mineralization hosted in the Corridor Selwyn domain. It's been dated at around 15 million years by Duncan et al. In 2011. It was done on sand mineralization molybdenite. It's a rhenium osmium age. And it's located, the SWAN deposit is located southwest of the Mount Elliott deposit, and I'll show you an image in a minute that talks about this. One thing that struck me when I started to study this deposit is that the size of it, like the current resources is 317 million tons at 0.56 copper and 0.34 grams per ton gold. But really, when you look at the total metal contained is around 1.78 million tons of copper. And if you compare that to Ernest Henry, it's 1.84 million tons of copper. So in terms of contained metals, this one Mount Elliott system is very similar. What we wanted to do for our mineral chemistry is we wanted to understand the geology. We wanted to understand the paragenesis to be able to put our vectoring phase or the minerals that we're targeting to a specific paragenic phase. If were they early, were they late, were they targeting mineralization, or they were minerals or all related to mineralization. So what we've done from the start is we did a geology model of the area, of the SWAN area. And what you see in the image on the right side is a scale here at the bottom. It's a kilometer of that scale. And what we've done is we've simplified all of these geology. There was around 30 different geology or logs that were recorded for the holes. And as we started to simplify them, we actually saw there was some surfaces that were starting to appear. So you can see them. This was done using Leapfrog. And basically what we see at SWAN is from the northeast to the southwest, we have a series of quartz mica schist interlayered with a basalt or metal basalts in green. And then where the mouse is there's another layers of quartz mica schist that's hosting the Mount Elliott. And corbel mineralization, this is where you have these pink interlayers here that are mapped as SWAN, as skarns. And below this, what you can see, if you combine all the calc silicates and the breccias and the marble intervals, you can actually end up with a really nice clean surface that forms this. And what's intruding the carbonates is the SWAN diorite. That is in gray here. And one thing that was not expected when we did the geology model is that green blob that's sitting in the middle of the deposits is kind of discordant to the different surfaces we've created. And we have mapped this as a mafic intrusion sitting right in the middle of the system. If we look at where this intrusion is compared to the mineralization, we have made our own ore shells in Leapfrog as well using the EDGE module. In yellow, you have the Mount Elliott carbide surfaces. It says 0.25 copper equivalent surfaces. And in red, you have the SWAN surface. So what you can see here is that the Mount Elliott is located right next to an apophysis in that intrusion. All right, so it's spatially associated with that apophysis, really, really close to it. And if you look on the SWAN deposit on the right side of the image, that red blob here is just flanks that mafic intrusion to the southeast. So there's a strong spatial correlation between where the mineralization is and where this mafic intrusion is. We're not too sure if there's a genetic link or not at the moment, but all we can say is there's a strong spatial correlation between the two. We've also done paragenetic studies at SWAN. We've looked at around 75 samples or so. And basically, this is the paragenesis that we came with. There's two main type of stage. There's an early stage that's going to reduce and sulfur poured, consists mostly of anhydrous silicate, which you have a sodic phase, which is albite and scapolite. It is followed by a more prograde phase, which you have diopside, garnet, magnetite, titanite, and alunite, which is the rare earth rich epidote. And this is followed by a more oxidized and sulfur-rich stage, which we see the apparition of hydrated silicates. You start to see a bit of apatite, actinolites, epidote, and there's anhydrite that we've seen kicking around as well: pyrite, chalcopyrite, calcite, K-feldspar, and chloride. All right. And I just noticed on this slide here, the boundary between the reduced in green and the oxidized in red should be where the prograde line is. So just a bit more to the left. So just some examples here, we have some laser ablation mounts that we've made. What we've done is XMOD, it's crystal mineralogy. It's very similar to TEMA. And basically what we have here is mineralogy by color. So what you can see in that mount here, we have in the background on each side of the mount is this light blue color, which represents albite, is overprinted by this bright red color here, which is a diopside, which is pyroxene. And this pyroxene is cross-cut by a magnetite vein in black. And this vein here is again cross-cut by a later vein, which is calcite in blue, chalcopyrite in orange, and pyrite in yellow. So this basically that assemblage which starts with from this early anhydrous silicates towards this more hydrous and sulfate rich. All right, so the next phase here, what you can see as well is in the background here, you have this dark red and red, which is scapolite and pyroxenes or diopsides that are cross-cut by this vein or this mass here that is green, which is amphibole, which is actinolite, chalcopyrite, and pyrite as well. So basically, any example I'm going to show you here for the mineral chemistry we've done is I used the amphibole, and you can see here that the amphibole comes a really similar timing as the mineralization. So basically, in these graphs here, what we have here is elements on the y-axis, and the x-axis for these 4 plots is distance to the closest 0.25 copper equivalent surface that we've created in Leapfrog. So the pink zone in these diagrams is the mineralized area. So if we're inside that ore zones or that 0.25 copper equivalent surface, you're going to fit in that pink area. So what we've seen for amphibole, as you move away from the deposits, we have samples from 0 to around 600 meters. And we also have one drill hole that's 1.5 kilometers apart. And what we can see for this is the vanadium, the chromium, and the strontium in amphibole decreases with distance to mineralization. Right? And manganese shows a profile that's a reverse to that. It's kind of a U-shape type of thing, kind of exponential growth. All of these are log scales, just for simplifying and make these plots a bit more visible. All right, so we've done that for all the minerals I'm talking about. We have done that for pyroxene, magnetite, apatite, amphibole, pyrite, epidote, and chlorite. And basically, the shapes of the profile is dictated by these things. So if you go back to the amphibole, on top that I just showed you, there was a vanadium, chrome, and strontium, which is on the top right here. They tend to be greater concentration towards the mineralization, which is the center of the screen, and it decreases as you move away. So the mineralization here, how you read this plot is that 0.25 copper equivalent shell is the blue. The dark blue, the breccia, calcilicate, and skarn outline alteration that was done from the drilling and the logging is in red, and the background here is geology. So you can see that the mineralization is mostly hosted in the marble, but it's also hosted a little bit in that mafic intrusion as well. All right, so that's all I have to say for SWAN. I'm going to give the microphone to Max so he can talk about Starra deposits.
Hello, everyone. My name is Max. I'm doing my PhD on the Starra deposit, which I commenced in late 2019. The Starra deposit is located just south of the SWAN deposit, which Jonathan just talked about, and somewhat north of the Ostwan deposit. It was dated at 1568 by Duncan et al. 2011, showing that it's quite a bit older than the SWAN deposit. We zoom a little bit into the. We zoom in on the local geology. You see that the Starra deposits are a couple of deposits that are emplaced along the Starra shear, roughly within like a 6 kilometer long interval. The southernmost deposit is called Starra 222, and the northernmost deposit is Starra 276. And I've overlain over the Starra shear the total magnetic intensity, which shows that the clear correlation between the emplacement of those deposits and magnetite in the Starra shear. If you look, for example, at the Selvin shear, which hosts hematite-dominated ironstones, there's no deposits and no magnetite either. And in this talk, I'm showing mostly rock photographs from Starra 222. The next slide. If you look at the paragenesis early on, we see a lot of amphibole. Here in dark green, we see some magnetite, which is the black color, some anhydrite in the orange color, together with pyrite. And all those minerals are overprinting here in bright blue, albite, and some plagioclase. If you go a little bit later or progress through the paragenic stage, we see that there's epidote coming in with large euhedral pyrites. There's some calcite, still a little bit of magnetite here in black, and some amphibole left. And dark red color is K-feldspar. We're relatively deep down below the ore zone at Starra 222. If you go further up Hohl into the later stages of the potassic iron alteration, you can see that there's quartz, calcite, and chalcopyrite veins following earlier chlorite veins. There's in the alteration halo around the veins quite a bit of silicification going on. And it's again overprinting the earlier albite alteration, which you can see in the rock photo with this reddish color. If you now go into the main mineralization, that's the typical Starra mineralization. It's an ironstone. There was earlier on the question about specularite. You can see here some of the specular hematite in the ironstone, pretty closely associated with chalcopyrite mineralization. There's still some pyrite left and a little bit of chlorite and quartz in the gray color. If we go to the later stage of the mineralization, it's in the hanging wall to the ironstones. You see on the right-hand side those carbonate crackles, calcite crackles, as they are usually called. They contain quite a bit of anchorite. It's this bright red color. There's a lot of barite in this dark blue color. The alteration halo is mostly K-feldspar and muscovite. Muscovite is the green color. K-feldspar is the skin color. And there's some chalcocite and bornite as well associated with that vein or carried on that vein. If we look closer at this Starra 222 mineralization, at this rectangle up here, it's the reflected light photograph. We see there's chalcopyrite coming in after pyrite. There's quite a bit of hematite in there, which in the case of, if I call it hematite 1, there's usually some relic magnetite in within the hematite. There's some barite down here on the vein, cross-cutting the pyrite. And if we look at this little square up here under the SEM, we see there's quite a bit of free gold coming in as well after the pyrite, together with some bornite as well. And this is later overprinted by more chalcopyrite. If you look at the late stage mineralization on those carbonate veins, you see again those chalcocite bornite assemblage carried on the vein. And interestingly, we see here those little bright minerals or element. It's native bismuth surrounded by bismuth-rich chalcocite. That's another bornite carried on the vein. Did like a laser ICP-MS image of that bornite, and it's quite rich in gold, tellurium, and bismuth. So there's a clear correlation between those three elements and mineralization. Now look at the Pyrite Chemistry. On the right-hand side in this graph, I plotted all the pyrite images I made. I think roughly around 30 pyrite images from the Starra line, which amounts to 150,000 pixels in this graph. And what stands out is the very high cobalt concentration, commonly above 1% in the pyrite, which is something we see for all the IOCG systems in the Cloncurry district we looked at. And there's this general trend among the pyrites from this high cobalt nickel ratio to a somewhat lower cobalt nickel ratio where the nickel becomes higher. It's a similar plot to what Jonathan showed you earlier. So it's the distance to the 0.25 equivalent copper grade shell. It's either Starra 276 or Starra 222, whichever is closer. We see that there is like a slight increase in gold inclusions in the pyrite when we come closer to the ore zone. And interestingly enough, there's the selenium in pyrite decreases when we come closer to the ore zone. Selenium can be an indicator for more oxidizing conditions in the during pyrite formation, which is a good thing that the pyrite seems to record those geological processes. Now look at magnetite. First here, it's the Starra magnetites. I've done like principal component analysis, and it pulls relatively well apart the magnetites which are far away from the mineralization in the darker color, and the brighter the spots are, the closer they are to the mineralization. And we see that mostly elements that are sensitive to redox conditions are the main discriminator in the PCA. For example, vanadium and chromium are strongly associated with the first principal component, indicating that Starra is mostly a redox-driven system. If we look at magnetite from Ernest Henry, Starra, and SWAN together, there's more or less a trend which can be associated with IOCG mineralization. It's this pronounced decrease in vanadium concentration and a slight decrease in gallium concentration. Whereas, for example, at magnetites from the eastern hematites at Starra, which are barren, you see no decrease in vanadium, or very little decrease in vanadium, and a more pronounced decrease in gallium. And those Ernest Henry samples on this trend are relatively distal samples. That's me, and now I'll hand over to Jeff.
Thanks very much, Max. Hello, everyone. We'll get you to the core shed in time, don't worry. So real quick through Ernest Henry. It's the largest IOCG deposit in Cloutier district. You all know that. You all know this too. Ernest Henry Geology. It's a big breccia pipe bounded by 2 shear zones. Wonderful. Drill hole locations. You've already seen these too. So I can just skip through half my talk and you guys will be there in record time. No problems at all. We're going to focus mostly on samples from this cluster here, close to the ore shell, but we'll also take a look at some of these more distal ones. The paragenesis at Ernest Henry is complicated. There's lots of minerals. They all formed at varying times. Today, we're going to focus mostly on the second stage of hydrothermal alteration, bleeding over into the third stage of hydrothermal alteration. Specifically, we're going to spend our time with rocks like this. So on the left, we've got a sample from FTCD 2435, which is kind of sort of 3 kilometers northeast of Ernest Henry. We have a lovely calcite epidote vein cutting through a red rock altered volcanic rock. And there's a little bit of chalcopyrite and pyrite intergrown with the epidote. And over here on the right, we've got a rock that's somewhat closer to the mine, comes from EH942, but fairly deep down hole. So it's about 500 meters outside the ore shell. Again, an epidote vein cutting through a red rock altered sample with some black actinolite, as well as minor chalcopyrite and pyrite down here in this corner. For ore, this is my sample that I go to and show. The ore sample, the ore material, which you've seen somewhat already, looks like this in reflected light. We've got a magnetite K-feldspar matrix with abundant pyrite intergrown with the magnetite and a little bit of chalcopyrite. But then we have this high angle vein cutting that rock. That vein contains much coarser grained pyrite, coarser grained chalcopyrite, as well as plenty of quartz, chlorite, and specular hematite. So there you go, Lionel. There's your specular hematite. Moving on, pyrite fingerprinting. What does pyrite look like geochemically at Ernest Henry? It looks like this. There's always weight % cobalt flying around in these pyrites, no matter where you are in the system. And as Max mentioned a moment ago, it's like this throughout the entire Cloutier district. Locally, very locally around the Ernest Henry ore body, you can get cobalt concentrations that get up to above 10 weight %. I've only seen that at Ernest Henry, so that may be indicating something unique about EH that is not reproduced at other Cloutier systems. More study needs to be done. If we look at the similar sort of information, cobalt over nickel, there's our trend, what we're unofficially calling an IOCG trend. We also have a second trend developing that has lower cobalt and nickel, and the ratio between those two is kind of 1-to-1 as opposed to 10-to-1 or 100-to-1, which is more or less what happens in this end of the IOCG trend. This obviously gets closer to 1 weight % nickel and lower cobalt. That's just from Ernest Henry, Starra, and SWAN. If we look at the entire Cloutier district with over 1,000 analyses, it's the same story. But here we have that lesser trend a little bit more pronounced. This is the dominant trend all across the Cloutier belt. Speaks for itself. Now, about the district, the Cloutier district and those samples. Here they are. Thank you very much, Jim, for sending these samples. They really helped us to get started with this work. 150 samples, 21 deposits, prospects. We looked at a bunch of minerals, pyrite, chlorite, apatite, and something else. Anyway, all of it is in that link that we put at the beginning of the talk. You can find it later on your own time. Let's look at magnetite geochemistry real quickly. We've got aluminum over titanium versus vanadium over titanium. Purpose of this diagram is to show that nearly all the magnetites we were looking at are not magmatic magnetites. They are hydrothermal magnetites. And in particular, some of the magnetites from Ernest Henry have very high aluminum over titanium ratios and vanadium over titanium ratios. So again, the fact that this is all Ernest Henry and nothing else, except for maybe a couple from Osborne and Starra, indicates that maybe there's something unique about Ernest Henry that makes it stand apart from the other systems in the Cloncurry district. We did, however, find a little bit of magmatic magnetites. So, you know, it's kind of cool that you can still find these things floating around in amongst all the hydrothermal alteration. It didn't all get obliterated. Okay, vanadium over gallium in magnetite again. That's just to remind you of this barren trend, this mineralized trend. At the 3 deposits we spent the most amount of time at, this is what it looks like globally in the Cloncurry district. So it's a little bit messier, but we still see the same kind of trend. Interestingly, the arms of these trends are formed by the 3 deposits that we spent the most amount of time on. The rest of it's kind of hanging out up here, doing whatever it wants to do. So again, further work needs to be done on this to really flesh out what magnetite chemistry is telling us about the fertility of these systems. Let's go to some minerals that do tell us more about the fertility of these systems. At least we think it does. So we'll start with chlorite. Chlorite is one of the 2 main green rock minerals that has been developed as a fertility indicator and a trace element vector in the porphyry space for over a decade now. And we just had this wild idea. What if we tried chlorite and epidote at Ernest Henry, at SWAN, at Starra? Let's see what happens. Well, this is what we got. So zinc over manganese is a common diagram used for chlorite in porphyry settings to give you an idea about the fertility of an area. And in particular, these high manganese values that get over 1 weight percent and in some cases over 2 weight percent, these are really strong indicators of a giant porphyry system. So for example, El Teniente in Chile has really high manganese chlorites, but ours are higher. So that's kind of something interesting. Like I think El Teniente is maxed out at about 15,000 ppm or 1.5%. Ours get higher than that. Again, the regional scale stuff is all kind of clustered around down here. This little box indicates this is generally where metamorphic chlorite hangs out. So that's encouraging that there are elephants in the Cloncurry district, perhaps some that haven't been discovered yet, at least according to the chlorite. If we look at it in a different sense, we get more information. So titanium over strontium is a ratio that's used a lot, again, for chlorite analyses in porphyry systems. And this time it's not a fertility indicator, it's a distance indicator. How close you might be to a heat source is basically what it is. So we've got titanium over strontium on the y-axis and distance to the ore shell on the x. The gray shaded area is whole rock analyses done by Vlad and Courtney at GSQ. So there's 221 of those and then 186 spot analyses done by me. And you can see there's a correspondence between those 2 data sets, but in my data set, we get more variation, which is expected. It's a more finer scale technique. Interestingly, this is MMA3, so about 4 kilometers out or so. We get very low titanium over strontium ratios. So they're higher inboard, closer to the deposit. They kind of fall away, and then they start picking back up at MMA2, 5 kilometers or so out. So let's look at Epidote, the other green rock mineral. We've got titanium and strontium and zinc and manganese for chlorite. For Epidote, it's antimony over arsenic. Again, the higher the antimony and arsenic in the Epidote, the larger the system in the porphyry world. So again, we were like, well, can it be, is there a correspondence geochemically in the IOCG space? Yeah, there more or less is, we think. Ernest Henry samples routinely have over 100 ppm arsenic and almost 100 ppm or a little bit above antimony, which corresponds well to some giant porphyry systems in South America. We also did a little bit of Epidote work at Esperanza South, but I'm not really going to spend much time on that today. We don't have time. It's all in the report. I'd love to take your questions afterwards, like another day, perhaps. You guys have got enough to do up there anyway. Vectoring with Epidote. That's also was kind of interesting. We've got high antimony inboard, closer to the deposit, like within the ore shell. It falls away out to about 1 kilometer, which is where the density of our samples drops off. We have a big sample gap for 1 kilometer to the next drill hole, and then another big sample gap out to FTCD 2435, MMA3, and then finally MMA2. But the overall trend is this big U, where we're high inboard, we drop away middle, and then we start rising again. So that's interesting. Kind of indicates that maybe there's something 5, 6, 7 kilometers to the northeast of Ernest Henry that hasn't been drilled yet. We'd love to know. IOCG summary. So the SWAN deposit, as Jonathan showed, is spatially associated with the mafic intrusion. Whether that's a coincidence or has to do with the genesis of the deposit is unknown. There are similar intrusions at Starra. The mineral chemistry of, our mineral chemistry work shows relationship with distance to the modeled ore shells and a range of minerals, which is encouraging. Obviously, the mineral chemistry is complex, but there's correspondence between the different systems. And the trends in pyrite and magnetite chemistry, we think, can differentiate between mineralized and barren systems. So I'm now going to throw back to Jonathan so that he can tell you a little bit about the sediment-hosted copper work that we did and that specifically he did at Lady Annie. Thanks very much.
Yeah, thanks, Jeff. That was great. So I'll talk to you about the Lady Annie system, probably around 5 minutes, and then we'll wrap this up. I promise we're not going to be too long. But we wanted to include a bit of sediment-hosted deposits because we think what's happening at Lady Annie is actually quite interesting and have some implications for exploration. So the Lady Annie deposit is a copper deposit. It's hosted in siltstone, carbonaceous and pyritic shales, carbonate, sandstone, and minor tuff sequences. And this is what you can see on the map on the right. It's all in the blue colors. The age is around 1645 million years, and it's hosted in the Paradise Creek and Lady Loretta formations. So for the study, what we did is took 2 drill holes that were 1.4 kilometers apart. And we looked, there was not many major structures between the 2 holes, and we wanted to test the difference in carbonate chemistry between carbonate veins in the mineralized area versus in the distal hole. So next slide. So what do the rocks look like from distal to proximal? All of them are hosted in this kind of calcareous shales in the black or dark gray in the background. And basically the main difference, if you're distal, you see this carbonate, pretty much dolomite plus or minus silica veins. And as you move towards the deposit, there's more veins, but there's also this appearance of pyrite and chalcopyrite. And when you're in the deposit, which is the total right image, you have lots of chalcopyrite, totally some silicification happening in there, and potentially some brecciation of the rock. So the question was, can we differentiate between the 2 systems, between the barren and the distal pit? So this is the summary of the work. We don't have time here to show the whole work, but basically most of the carbonates that we found were dolomites with a subset trending towards anchorite pole, and you can see that on the ternary diagram on the right side of the image. There's also rare siderite presence, but not many. We found the carbonate veins, there was 10 generations of carbonate veins or dolomite veins mostly, and most of them can be differentiated through petrography, but also through rare earth patterns. So there's lots of very different rare earth pattern chemistry from this. But the main difference between the 2 drill holes, the distal and the proximal, was 2, I guess 1 mineral and 1, I guess oil, or that was sitting in there. There was pyrobitumen in the mineralized hole, and there was chalcopyrite in the mineralized hole. In the distal hole, you still had pyrite, you still had everything else that was there. And this is what I'm going to show you, what these things look like. So on the left side here, I'm going to focus on the green box first, which is the first generation of pyrobitumen. We found 2 generations. And basically you see these dark layers on the top left of that kind of rock slab. And there's a vein coming from this. And there's a carbonate veins. Within that vein, there's lots of dark bits. And this is where the pyrobitumen is coming from. So it might be derived from that little layer that's coming up top there. And basically, if you do an SEM image, which is the one in the center and the top, the darker gray ones is the pyrobitumen, and the bright one, the bright phase, is the carbonate or the dolomites. So what you can see here is that pyrobitumen is highly fractured. It really looks like it's just been entrenched in that carbonate veins, and it was almost solidified already by the time that this was happening. If you move to the second generation, which is the image on the bottom left here, you have the core and the BSC image of the slab. And what you can see is there's dolomite veins here that's sitting on the edges, and in the core of that vein, there's pyrobitumen. There's also quartz, and there's a different color of dolomite, which is that kind of bright gray color sitting in there. And if you do SEM image of these pyrobitumen, what you can see is there's a kind of a core. It tends to be a bit more globule, less brecciated than the other pyrobitumen. But if you focus on inset D, which is on the bottom right of that image, you can see there's been interaction of fluids, potentially a brine or something similar, with pyrobitumen that's somewhat digested the pyrobitumen, and there was definitely some interactions between the pyrobitumen and the fluid that formed the dolomite. So on the next slide, what we've done here, we've done some electron microprobe microanalysis, and the samples here, there's the colors of different samples. The green is the phase 1, and the yellow and red is phase 2 pyrobitumen. And the symbols here, when it's open, we looked at the rim versus if it's filled, we look at the core of these pyrobitumen. And what you can see really in these diagrams, if we start from the top left here, the iron versus sulfur, is that the rims of these pyrobitumen tends to be enriched in sulfur. So the open samples are enriched in sulfur, but it is also enriched in iron. Where we've seen there was detectable copper in the dolomite was only in the rims of these pyrobitumen. So there's starting to be a bit of copper precipitations in the rim. We didn't detect any copper past detection limits in the core of the pyrobitumen. If you go on the bottom right here, what we see in these two different samples is that the rim could be either less enriched in chlorine or depleted in chlorine compared to the core, but they tend to be still around 1,000 ppm chlorine. And the other thing that was interesting is the core of these pyrobitumen globules were hosting some nickels. We didn't detect any nickel in the core, but we actually found some nickel in the core of them, not in the rim. So could that be some interactions between copper-bearing oxidized saline fluids with pyrobitumen? So that's what these things suggest, is that there potentially be some interaction between the two, and it might have been important for precipitation of copper at the Lady Annie deposits. So very quickly, as a quick summary, is that the Lady Annie veins, similar about proximal and distal for mineralization. You can actually be able to visually see and chemically see similar profiles for mineralization dolomites. The main difference, like I said, is the presence of pyrobitumen and chalcopyrite at the deposits. And we see pyrobitumen interacting with this potentially copper-bearing brines that brought copper, iron, and sulfur. Is this a coincidence? Or it is part of an ingredient that potentially formed a Lady Annie deposit or some other ionized type copper deposits? All right, so to wrap up the talk, hopefully we're able to show you from the IOCG perspective that these are very complex. They're multi-stage deposits. They don't form just a one bang. There was a progression from a reduced assemblage to a potentially more oxidized assemblage through times. But if we use a mineral chemistry, we can use it to be effectively vector to mineralization. And we've tested that in the Cloutier province. We haven't tested that anywhere else, but we're expecting this will be working as well. There's chemical trends in pyrite and magnetites that can potentially differentiate between barren and mineralized systems. And from the sediment-hosted copper deposits, we saw at Lady Annie, like I just said, that there was carbonate veins 1.4 kilometers away that had the same chemistry, and pyrobitumen might be an ingredient that we want to look at for the formation of these type of deposits. All right, so we realized that we just bombarded you with lots of information. We decided to play our greatest hits today, and that's to show what we've done for an overview for the project. But if you're interested, we kind of propose to have a longer, potentially half-day workshop to discuss this in more detail and actually have the time to actually show our results. So if you're interested, you can email Jeff, Steadman at utas.edu.au. And it'll also be an RIC linkage proposal that's in the work that will build up on what we've learned from this and move on and push it forward in the next 3 to 4 years. So if you're interested as well, you can talk to Jeff about that.